In the last few lessons, we talked a lot about ethane, ethene, ethyne. Today I want to talk about something a little more fun. Let's talk about methylamine. Methylamine. You might have heard of this if you ever watched Breaking Bad. It's a precursor to methamphetamines, but when it comes to the actual organic chemistry of it, it's pretty straightforward. Methyl means one carbon, and amine means that it's bound to a nitrogen. So let's draw a carbon bound to a nitrogen. I think we could handle that together. Now, let's remember from the periodic table that nitrogen has this extra electron. It has 5 electrons we're going to have to account for here. So let's see what that might build like. Here's my carbon. And carbon likes to form 4 bonds, right? Hydrogen, hydrogen, hydrogen. And it's sigma bonded to nitrogen. And nitrogen has 2 lone electrons in its own orbital out here, and then it's bound to a hydrogen and a hydrogen. So that might seem funny at first, but if you look at it, these 2 electrons that bind hydrogen and nitrogen together in sp3 orbitals, and nitrogen's lone pair here has the same number of electrons as these orbitals, so it's going to form the same kind of hybridized shape. Whether or not there's 1 proton out here isn't that big of a deal. It does change things a very, very tiny amount, but nitrogen has 7 of these protons in here, so most of the positive effects are coming from the center of the molecule, not really the hydrogen, which is another word for just proton, right? There's 1 proton out there. That's all hydrogen is a proton and electron, right? See here. So a lot of times you might see something like H+, and that just means a hydrogen whose electron is gone, which really is just a proton. And don't confuse those too much, right? And then we have this sigma bond here, which is kind of like a football shape, a jelly bean shape. And carbon has its typical sp3 orbitals because, of course, it has 4 bonds. So that's going to be add up to 4. sp3 adds up to 4 bonds, 4 different atomic bonds. But one other thing that determines shape is this lone pair here that we haven't really talked about yet. And in nitrogen's case, I want you to notice it has 4 major structures here. It's bonded to 3 things, 3 separate sigma bond type things, and 1 lone pair of electrons. So he too is going to form something very close to what we call an sp3 orbital. I want to say that the actual angles of the tetrahedron, right? Remember drawing the tetrahedron out to get a better 3D view of this. You put carbon in the middle of it, and it reaches up here, and it reaches down to these corners, and that's where you would find the hydrogens. I want to say the bond angle for these in 3D space here is like 110, and these bond angles make 107, so it's very, very close. It's just there's a little bit difference. There's 1 different proton, and there's 1 different more or less of the electrons. They make a very, very slightly different thing. But still, nonetheless, you're going to see nitrogen here. And remember, we don't even denote carbon over here. And we don't denote the hydrogens either. So this is methylamine. How funny is that, right? But to fill it in for us as new students, let's just remember that we have this one. And let's say it's going into the page. So let's kind of draw that for going into the page. And we'll say this one's coming out of the page. So I'll fill it in. It's supposed to be totally filled in. Hydrogen, and then one that's even with the page this way. And that's totally chiral, which means it can swivel about. It can rotate on this bond, no problem. It's free to float around like a propeller. And nitrogen, it's 2 hydrogens. I'm going to say this one's like coming out of the page. We'll fill that in. But it could be going the other way. It's not that important. And we'll say that one's going into the page like this. And then up here, these lone electrons, you really are only going to see it based on what the others look like. So this is what you would see of the protons if you were to look at it in some kind of special 3D atom viewing microscope. But this lone pair of electrons here absolutely pushes away this electron set and this electron set, and it's also free to spin. It's chiral. It's free to rotate about. So you would see that there's no reason that these hydrogens would want to be close to this there's no reason that this electron bond and this electron bond would want to be near each other. These electrons repel each other, and the hydrogens kind of say like, okay, I'll float over this way then and I'll be fine down here and up here. They always want to stretch out to make the electrons comfortable in whatever way they can. And because of the 6 protons here and the 7 protons here, this sigma bond is very happy, but the protons are going to push each other apart a little bit. So you'll see a little bit tighter bonding between, say, hydrogen and nitrogen because it's so much smaller than the carbon and the nitrogen against each other. This distance will be just a little bit wider as a consequence. Okay, what if we pull up another example? Let's use another example here. Let's make another very famous molecule that you might have even heard of before as a non-student, methanol. Now this doesn't have an amine at the end, and it doesn't have an ane or ene at the end. It has an anol at the end. What's an anol? Well, that means that there's an OH group, oxygen, hydrogen. We call it an alcohol. There's a reason for it. It's very common, so it needs to have a name. And what does meth mean? It means 1 carbon. So you're going to have a carbon, and then you're going to have an alcohol group. Let's take a look at what that means. You know what? Let's move this up a little bit and out of the way. Why not? Methanol. Hope I spelled it right. It's not enough letters for me to have an excuse to spell it wrong. Methanol. Let's put our carbon on the right side, and then we'll make an OH like this. There's my alcohol, there's my all, and here's my meth. Okay, so we're good to go. Let's fill this in. Carbon needs 4 bonds, so it needs a hydrogen, and that one will go into the page, this one will come out of the page, hydrogen, something like that. And let's say since this one's coming out of the page, let's say this one's going into the page. Since they're somewhat near each other, we'll just say they have opposite directionality to be more apart. It's a good guess. Something like this. But also, oxygen has how many electrons? It's way over here. It has 6 electrons in this second energy level. We've accounted for 1, 2 of them. There's 4 more. And that is in lone pair orbitals out here, like this. This one's maybe going off in a different direction than this one, and this one, same tetrahedral concept, because the number of lone pairs, 1, 2, plus the number of bonds, 3, 4, is 4. So it's going to form an sp3, which is also going to be that tetrahedral general shape. That's exactly what that is. So even though oxygen's only bonded to 2 things, it's because its lone pairs are already kind of happy setting up its octet. It has completed its second energy shell with these bonds alone. We have all 8 electrons accounted for. So it's unlikely that these are going to want to really reach out and take more. You're not going to move up to the 3rd energy level without a lot of extra help. And in carbon's case, of course, 4 bonds, that's normal. So you're going to get sp3 hybridized orbitals over here, and you're going to see sp3 hybridized orbitals over here with methanol. Now, of course, these electrons do not show up on a microscope. You're going to see this if you can look at the actual mass of the atom. And if you draw the molecule, you're going to see it drawn this way. No one's going to show you these extra electron pairs out here. You're supposed to know they're there. You're supposed to know that. What else can we look at? Let's come over to something with a phosphorus maybe. Okay, now let's talk about methyl phosphate. This is going to get weird, and this is what I love about it the most. So far we've talked about wanting to complete energy levels, and we're talking about our octets, but now we're talking about phosphorus, which is down here in the 3rd energy level. And you may not remember right away, but after 1s and 2s and 2p, there's 3s, and there's 3p, but there's also 3d orbitals. And that's not 3-dimensional. That's another type of mathematical abstract idea, but you don't need to know too much about it. Let's just try and draw methyl phosphate and see what we get. Well, methyl means what? It means 1 carbon. You should know that by now. You hear methyl, you think single carbon right away. Phosphate is a common name for PO4, and I believe it's a -2 ion. So there's 2 more electrons than you would typically expect in a totally balanced system. And let's see what it kind of looks like. Let's draw it out. The first thing to remember, or the first thing to learn, you can't remember it if you don't know it yet, is that this carbon is going to be bound not to the phosphorus, it's going to be bound to an oxygen. And that oxygen will be bound to our phosphorus, which is bound to these oxygens, like this. Except phosphorus doesn't create 4 bonds, does it? Look, phosphorus has 5 electrons naturally. It's weird like that, like the nitrogen we just looked at. There's going to be some funny business going on here. And in fact, this phosphorus is double bonded to 1 oxygen like this. But let's look at where the electrons are to kind of understand what's going on here. Oxygen has 6 electrons in its second energy level that are available for use, so this oxygen has used 2 of them, which means it has 2 out here like this. And sure enough, those orbitals look like this, and it should actually appear to be an sp2 type of hybridized orbital because it's bound to 1 plus 1, 2 sets of lone pairs. Well, that's 3, and sp2 is 3. So if it was bound to 4, like this phosphorus here is bound to 4 different oxygens, will exhibit sp3 shape, which means it should have that tetrahedral kind of shape. Put phosphorus in the middle and our oxygens would be at the 4 corners like this if you were to draw that stick figure out like that. But there's weirdness here, right? Because we have a double bond and oxygen has 6 electrons. We've only used 1 here. And in fact, 2, 3, 4, we're going to put 6 here because oxygen needs to complete its octet to be happy. In the second energy level, we're not messing around. You need all 8. You really do. So this oxygen over here actually has 1 extra electron, so it's kind of a negative space here. And same for this guy. He has the same setup. He's going to have a negative charge on him here. And oxygen's very famous for this. Electron's a slut. Let's just be honest about it. Oxygen steals electrons from everything. It's so greedy. And in fact, it's a major, major factor in how life can even exist. This oxygen it's a compulsive thief. It's a kleptomaniac prostitute. It's insane for electrons. Just the right amount of protons, the right atomic radius. It strips electrons off of everything. I don't know if you've heard the term oxidizer before, but it means I'm taking electrons. That's for dang sure. Now this oxygen here, lone pair, oxygen here, or electron pair here, this is going to be sp3 also, or sp3 also. So you're going to see tetrahedral. Maybe this one's up and these 3 form the pyramid, however, depending on your orientation. And same with the carbon. Here it's bound to 4 things. There's no lone pairs over here, but 4 bonds. So he's going to be sp3. Everything in this is going to be sp3 hybridized. But there's something else I want you to notice. This phosphorus with its 5 starting electrons, you see all 5 are bound here, which means it's connected to 10 electrons, not 8. And it's because of those d orbitals that I've left out of our periodic table here that are typically existing in heavier things like iron and gold and silver. Well, phosphorus has access to that 3D style orbital at this atomic mass. And you can think of it as saying it's got 15 protons. That's enough positive charge to be willing to attract maybe 1 or 2 more electrons than 15, where they're all willing to take just a little bit less than 1 proton each. They're a little bit hungry, they're a little bit lean, but they're willing to do it if they form the right configuration. It's not perfectly stable, but when you have oxygens in all 4 directions, oxygen is going to pull electrons just a little bit away from the phosphorus as well. And that again leaves a lot of open space for electrons to kind of fit comfortably together. So you can expect that oxygen pulling in all 4 directions here is part of what makes it allowed. But there's something else I also want to point to, is this double bond. There is no reason to believe this double bond is here. It could easily be here, or it could be here. None of these oxygens are any different than the other. And in an experiment, what we find is that this double bond is actually kind of not totally anywhere. It's harder than that. Let's draw it this way. I'm going to draw it as a dotted line. And I'm going to draw this as a dotted line, like this. And I'm going to draw this as a dotted line, like this. Because those last two electrons and that double bond kind of bounce all over the place. They call it delocalization, which means these last two electrons, this double bond, we know is there. We know that phosphorus is forming that fifth bond, but it seems to be bouncing around between these three different electrons. You won't find it in a specific necessary spot, and there's nothing in this atom, or sorry, in this molecule to indicate that it should necessarily be here. Like if this carbon was attached to like a big giant iron or something right here, maybe it would force something to happen over here, but this carbon is totally symmetrical in all directions, and it's chiral, it's happy to rotate around. So this situation, you do not have to think of it this way. You could have drawn the double bond here, you could have drawn the double bond here, but ultimately what you're going to find is that for these oxygens to complete their octet, they have to have an extra electron, and that this -2 configuration for the entirety of this molecule is going to live over here on the phosphate side of things. Carbon doesn't have room for that. Phosphorus is big enough, and he's being pulled in all four directions by oxygens enough to where there's a little gap space for these last two electrons to fit in. And though that isn't something you need to really understand right now, you should be able to tell me that since phosphorus is bound four ways, like this, that I'm going to get sp3 orbitals. And this oxygen in the middle has two sets of lone pairs like this, which means it has 1, 2, 3, 4, and that means sp3. That means tetrahedral, same as the phosphate was. And same for this carbon over here. No lone pairs, but 4 total bonds, also sp3, which means this entire molecule is going to be close to sp3 hybridized. To watch this full playlist in order, click on the video here on the left, or to go to the next video, just click on the video here on the right.